Hello guys, welcome back OpenFOAMers to this next video of our turbulent pipe simulation. So now we've been going through lots of PISO foam before. It uses the PISO algorithm, and the next thing we want to take a look at is this thing called the pimple algorithm. The pimpleFoam algorithm, which you can find in the tutorial. Alright, so I was navigating there just now, so let me clear this up. CD foam tutorials. From tutorials and go to incompressible and go to pimpleFoam. It's very important to understand what this pimpleFoam does, because that's also what you will find in, that's the solver you will find in the OpenFOAM heat transfer solvers, especially for convection. They use this pimple algorithm. So before you want to go and use those buoyant pimple foam, it is very useful to see what pimple foam without all the heat transfer equations, what does it look like. So as per normal, you have the LES, the large eddy simulation, the Reynolds average, Navier-Stokes, and of course the laminar flow cases. We usually like to go to RAS because that's the most basic turbulent model. And for basic pimple foam, we can go into Pitt's daily. It's a very common case. It's very well studied. So if you take a look at the system file, go to FV solution, we can see that, well, as compared to, let's say, what we have in our turbulent piso-foam snappy pipe, or our turbulent piso-foam snappy pipe or refined piso-foam snappy pipe cases. Refined snappy foam pipe cases, we can go to the system directory and we go to FV solution. Right, FV solution. Okay, you take a look at this. We see the differences here. We have the solvers. One solver for the pressure kind of a thing, pressure matrix, a pressure system of equations that they are solving because they are using a finite volume method. And P final, what's the difference between pressure and P final? We can talk about in the coming videos, because it's you got to kind of understand how the algorithm runs. Then you have the UK epsilon omega r nu theta. All of these are all the what do you call that? These are all the turbulent parameters that we're talking about. Okay, U is the normal, average velocity, and all the rest of these things belong to the turbulence modeling part. Same as well here, you have a K epsilon model, which you have a K epsilon model along with you. You use this kind of solvers with the tolerance settings, and now we want to take a look at the difference between piso-foam and pimpleFoam. These inputs, okay, in the piso-foam we have the N characters and non-orthogonal characters, and then this P reference cell, P reference value. In the pimpleFoam, as compared to that, you have the N non-orthogonal characters and N characters. And of course, if you look at other pimpleFoam cases, let's say propeller. So I've run this before, so let's VI system, FV solution. We take a look at the other cases of pimpleFoam. We see that the pimple directory has a correct phi, and outer characters, and characters, and non-orthogonal characters. So this one is usually what is different from the piso-foam. that this n outer characters separates the pimpleFoam algorithm from the PISO algorithm. How does it do it? I'll be getting to that in a bit. And of course, there's this other thing called relaxation factors you might have seen in some cases. So we'll go through some of that as well. And before we do all that, I want to kind of, copy and paste. I want to copy and paste a lot of the old pimpleFoam case and make a pimpleFoam case in this directory. Yep, so let's see. Clear. And I want to do a CPAR refine snappy foam piezo pipe. And I want to put pimpleFoam snappy pipe. Okay, so that's pimpleFoam snappy hex mesh in a pipe flow. So let's just do that. It'll take a while to copy and paste. Hopefully I have given it the right syntax. Okay, so while it is copying, and it's gonna give a lot of it's gonna take a lot of time to copy all of that around. Okay, but I can just ignore that. Yeah, it'll take a lot of time to it's taken a fair bit of time to copy that around, but we can take a look at what we have here. We have now the pimpleFoam snappy pipe file, which we can proceed to go into, and we can start modifying some of the things there in order to do our pimpleFoam case. So I'll do an all clean, and I'll do a git add and git commit with a message starting pimpleFoam case. Okay, now push it up to GitHub. It's gonna take some time to add. I will just now so what is the difference between pimpleFoam and pimpleFoam? Now first thing first, we can get an answer to that by coming to this OpenFOAM wiki. It is called the OpenFOAM guide, where they talk about the pimple algorithm in OpenFOAM. So I'm going to copy and paste that here into this Word document, where I'm using it to kind of discuss what it is about. So as with all computational fluid dynamics algorithms, there are two basic equations you need to solve. Okay, so one is the momentum equation. Okay, there are two fundamental equations you need to solve. One is the momentum equations. Two is the mass conservation. So in incompressible flow, that is what is that? Yeah, that is continuity. Yeah, continuity equation. Alright, so let me find the formulas. Alright, so I pasted all these formulas in here. So if you've gone through the derivation of the Navier-Stokes equations before, you should be pretty familiar with this. So the equations that we're solving here, these are the momentum equations, and this is the continuity equation. Alright, so if we take a look at what is being done here. Okay, I'm not going to go through this yet, but this is very useful thing. I'll come back to it when it's more relevant to discuss that. But we'll get to the fundamentals of the algorithm first. Yeah. So I'm going to get through the fundamentals of the algorithm. But before that, I want to give credit to this guy. His channel is called Fluid Mechanics 101, and he talks about the simple and the PISO algorithm, which are being used, and they are very, very useful if you want to go a little more in depth and kind of have a crash course. So I highly recommend you subscribe to his channel if you want to talk about know more about algorithm. I'm doing it in a very touch and go manner so that you can use OpenFOAM ASAP. But if you want more in-depth understanding, I highly recommend you go visit his channel. So Fluid Mechanics 101. Yes, so one of his video links is here. This is the simple algorithm. Okay, and the other one is called the PISO algorithm. CFD Fluid Dynamics 101. So I want, do go and visit his channel and support him, subscribe. So that's the PISO algorithm. Both of these are very important to understanding the pimpleFoam algorithm. So these are some of my references. Okay, so yes, all right. So basically, we have momentum equations we need to solve, right? Momentum equations that need to be true with, it has to satisfy this continuity equation. So what is the method of guessing usually we do? All right. Usually for numerical solvers, we need to provide an initial guess of pressure and velocity field. Alright, hopefully that's not too foreign to you. You should know a little bit of numerical methods. Alright, so you need to provide initial guess of pressure and velocity field, and for iterative solving, we need to substitute back, iterate until we get convergence. Means we approach a solution. Approach a solution satisfying all equations. So this is basically the method of iteration. Should be very familiar, so I'm going to leave it as it is. So what do you usually start with? So let's say we start a solution methodology. This is called algorithm. So it provides us systematic steps to solve these equations. First, we need to guess give you a random guess of velocity and pressure fields. Right? So that gives it the initial guess. Right? We initially give an initial guess of this, and then secondly, we fit them into the momentum equation. Right? So we fit them into this equation. Okay? And what is the goal of doing that? The goal of which is to get a velocity field satisfying the momentum equation. So what we are doing is that, okay, we get a field here. We have the pressure field, so P, X, Y, and Z, and we have an initial guess of both, and we want to get a velocity field knowing U, V, and W everywhere. The three components of the velocity field in every direction. So what we do is that we fix the pressure field guess right? We fix the pressure field guess, iterate until velocity field reaches some kind of it reaches a converging solution, some kind of solution. Okay, so we have a new velocity field. Alright, so this is very important. We have a new velocity field that comes from here, and then of course we want that velocity field to satisfy this equation, which is the continuity equation. So new velocity field, which I'll highlight here, must satisfy continuity. So what do? Substitute the velocity field in. Substitute the new velocity field in. Check if that's the next step. Check if continuity equation is satisfied. So what happens next? If new velocity field fits, good. Okay, so if the new velocity field fits, the new velocity field is the solution. If it does not, this is not the solution. And what do we do next? So we need to have some form of new guess. And then we need some new guess for the pressure field to get another guess for the velocity field until we find a solution which fits both momentum and continuity equation. So what we basically done is we guess the pressure, we set an initial pressure field, and then we get a velocity field from this by solving these three simultaneously, and the OpenFOAM solver or whatever numerical solver will do it for us, and then we will substitute all of this into this continuity equation. Unfortunately, the only feedback that this continuity equation gives us is it's only a yes or no answer. So if the divergence of the velocity is 0 everywhere, then you can say, okay, it satisfies continuity equation and it solves it. But if it does not, then we have no idea what the next guess of a pressure field is. You'll kind of have to guess like a million kinds of pressure fields or many different combinations just to get you try and guess and check, So what we are doing is this, it's just guessing and checking. Okay. This is class notes. So I'm basically, this algorithm is I'm guessing a pressure, and I hope the velocity field fits the fits the continuity equation. So let's say your true velocity is here. That's your target, right? This is your target. So what you're basically doing is playing a game of blind darts. So I'm guessing another pressure field. I somehow hope that the velocity field satisfies continuity, but more often than not, it will not. So the problem is we kind of need a new guess for pressure, right? A new guess for pressure field based on the feedback that the continuity equation gives us. Unfortunately, in this form, the continuity equation will not give us any kind of feedback. Okay, it will not give us any kind of feedback on what your next guess of pressure should be. Okay, so ideally we want feedback to say, based on this new velocity field, what is my next guess of a pressure field? Right? So that is something we need, and we can discuss more of that in the next video.